Good morning, my student. Welcome to my class. Today, we are going to talking about the chapter 2. On the chapter 2, I would like to give you some suggestion before we start on our study of chapter 2. What we're going to have on chapter 2, let's go to our textbook. On the textbook, you may see on the chapter 2, we gonna have 6 items to study. One is the idealized structure. That's how do we change the real structure to the model that we can use our theory and mathematics to solve it. And then we're talking about the principle of superposition. You may recall from the final examination of mechanics of material. Problem number 4, we have a beam. This beam can be separated into 2 simple beams. We like to find the maximum deflection of the beam on the examination, and then we can find the total deflection by finding the reaction from the 2 separate beams. And finally, we use the principle of superposition to combine them. On the item 2.3, we are talking about the equation of equilibrium. You may recall again, for the analysis of the beam, of the frame, of the truss, we need to prevent the structure from moving horizontally. That means the summation of force in the x direction is 0. And then the summation of the force in the vertical direction, which is the summation of f sub y, is equal to 0. And the last one is the summation of the moment to prevent the rotation is equal to 0. So that means we can solve the structure in 2 dimensions with 3 equations to get 3 unknown. And next, we're going to talking about the determinate and stability of the structure. The structure that can be analyzed by using the free body diagram and the equation of equilibrium, we call the structure statically determinate. Most of the structure that we have until now is statically determinate. In the opposite, if the structure has a lot of support, as you may recall back to chapter 4 of the mechanics of material, you cannot only use the equation of equilibrium to analyze the structure. That means you got to put the compatibility condition to help to assist the equation of equilibrium to analyze structure. So to separate the structure into statically determinate and statically indeterminate, we got to check the determinacy of the structure. And then what about the stability? Stability is the ability of structure to stay there, to resist the applied forces. The structure that lack of stability, such as the chair, if the chair have the wheel, and then you apply the horizontal force to the chair will move horizontally. That means the lack of stability in the horizontal direction. And then we come to the 2.5. The application of the equation of equilibrium. We're going to use the knowledge of 2.3 to apply 2.5. And 2.5, you did a lot of calculation on this in static already. We draw the free body diagram of the structure. We apply the equation of equilibrium, and then you get the reaction of the structure, for example. And we will skip the 2.6, the shear wall system. We are going to talking about it in the other course. And then after vision point 3, we will apply what we have, the free body diagram and the equation of equilibrium in chapter 3 and also chapter 4. Okay, that is the first part of this. And then I will send you the lecture note on these two chapters. And let's see, what is this? Oh, okay, it's here. And I hope you guys are going to use this PowerPoint as the main part of our study. Okay, I will put this PowerPoint for you guys, and you may use it while you take a look at my clips. And also we will have some example in which I'm going to write you the detail, show you the detail of calculation. This used to be one of the problem in the examination. Is talking about distributed the force. So I like you guys to be concentrated on this also. And then I will provide you the homework, okay, for you to have a chance to do the practice. And okay, that's all for my introduction to the chapter 2, and I will produce the clips follow what I'm saying. Okay guys, hope to see you at the next clip. Bye. Hello. Okay, let's go to the chapter 2. On the chapter 2, we are going to talking about the analysis of statically determinate structure. And the objective of learning that we going to have is the use of the free body diagram, the equation of equilibrium. You have used these two things many times already since the ending static, and we are going to like you to have more skill on this. And also we will use the principle of superposition in the analysis of statically determinate structure, the beam and the frame, as you can notice from the picture. This is the beam, this is the frame. And then we like you to understand and be able to determine the determinacy and stability of the structure. We need to find the determinacy because in the large picture, the structure can be separated into statically determinate. That means we can solve the structure by free body diagram and the equilibrium equation. And the other is the statically indeterminate structure. In is no. That means the free body diagram and the equation of equilibrium is not enough. We got to put the compatibility condition to show that kind of structure. Let's recall what we have on the chapter 4 and chapter 5 of the mechanics of material. We have this before. And then we check the stability. That means we check that the structure will be static by resisting the external applied force. And the chapter 2, we will have the problem in the midterm examination. Is going to be two problems, the two small problems in the one big problem. One is going to talking about how we distributed the force before we apply the equation of equilibrium, and the other is the linearity 2. So in conclusion, we will have examination from this chapter, unlike the first chapter. In the analysis and design of structure, one duty the civil engineer is supposed to do is simplify the structure into the one that we can analyze. And also we need to recognize the assumption that we use in the analysis. Let's consider the stress strain diagram of the steel. This steel have no yielding, so we use the 0.2% offset to determine the yielding of 352. In the design, you have learned that we didn't use this value. We will divide the yielding stress of the steel by the factor of safety 0.2 by 2.0. That means actually the behavior of the steel is going to be in linear elastic portion. The same thing, the concrete. We didn't use the ultimate stress of the concrete in the design. We may use only half of that, that is about 20. And you can see from this curve is linear, right? So the main assumption is the behavior and mechanical property of the material is linear elastic and follow the Hooke's law. That means the stress is proportional to the strain, or the stress equal to modulus of elasticity times the strain. And the second thing, the structure in the application of the force will deform very small. If it's deformed large like this, crack will occur into the structural member, and corrosion or the moisture may react with the steel and get lost. We will prevent this large deformation. So in the design of the beam, if there is no wall, we will limit the deflection to L over 240. If there is a wall, we limit the deflection to L over 360. That means if there is wall, the limited deflection is going to be smaller than no wall, because large deformation of the beam also cause the crack of the wall also. And then this means we got to do that. And the factor of safety also important, not only due to the behavior of the structure, is maybe due to the unexpected phenomena such as the earthquake and the wind. Also, it's going to support the construction error that may occur for some time. Next, we also need to model the connection and the support, not only make the assumption of the linear elastic behavior and the small deformation. On the structure, there are two parts that you're going to need to make some assumption. And when you decide, and the final state of design, you got to detail those kind of joists and support in accordance with your assumption. Mostly, if you model the support as the pin support will not have much constraint, okay, like this, compared to the fixed support that you're going to fix this. You're going to put a lot of bolt. However, the pin, you don't need to.
and the symbol of the fix is this, of the pin is this. Talking about the joints, we have two types, rigid joint. That means you put rigidity into the joint, you weld it, you cast the concrete into one piece. That's going to have the symbol like this. However, if you allow the joints to rotate freely, you may assume it as the pin, and the symbol is like this. So it's up to you as the engineer to assign the connection and the support into the structure. However, you got to decide, no, you got to analyze it and then decide it in accordance with whatever you make the modeling. Okay, this is important. This is a real picture of fixed joint, the really strong rigid joint. It cut into one piece. This is a picture of pin support, and this is a picture of the roller support. This is the big girder. Why they going to build this as the roller? Because during the daytime, temperature is high, right? The beam going to be expand. However, at the night time, the temperature cool down, the beam going to contract. So they're going to allow the connection to move a little bit to accommodate what we have due to the temperature change. And the last one is the fixed connection. You can find this in front of our library. In conclusion, this is the pin, and the pin as shown here have the symbol here. By having symbol here, that means this pin resists the force vertically by preventing the movement in the vertical direction. However, in the horizontal direction, it can move freely. So that means this roller, not pin, this roller have the reaction like this. For the pin prevents the movement in the horizontal and in the vertical, but allow the rotation freely. So the pin going to have only two reaction, no movement. The fix won't allow the movement in horizontal, in vertical, and rotation. So the fixed support will have the horizontal reaction, vertical reaction, and also the moment reaction. Okay, this is the real roller support. This one for the steel. That means it allows horizontal movement of the steel beam. Over here is a concrete. It allows the horizontal movement of the concrete beam. Only the reaction in vertical. Only the reaction on the vertical. And then the model going to be like this. For the pin support, we put the bolt to fix this into position. The pin support allow the rotation, but not allow the movement. So the pin support will have the reaction in the horizontal and the vertical, and no moment reaction. The fixed support, they are going to fix together, no movement at all. So the reaction can be F sub X, F sub Y, and also the moment reaction. Okay, that is the first part. I just mentioned about the objective of learning. I mentioned about examination. This chapter will have one problem with two small sub-problems inside it. And the examination is going to talking about the distribution and force and how to determine the determinacy and stability of the structure. And then I'm talking about assumption to analyze and design of structure for the linear elastic and small deformation. And then we have talked about the modeling of the support that can be hinge, that can be pin, that can be fixed. the hinge only have one reaction force. The pin have two reaction force because pin prevent horizontal and vertical movement. The fixed have two reaction force and one reaction moment because the fixed won't allow horizontal and vertical movement and also won't allow the rotation. And also we have the joists. The joint can be separated into two types, rigid joint and a pin joint. And the most important is when you model the structure, you got to analyze and design by using this model. And finally, when you produce the detail of construction, you also need to do that. Okay, this is the first part of chapter 2. Okay, on this slide, we're going to apply the previous knowledge into the molding of the steel frame. This steel frame is statically determinate frame. This is the actual structure, and this is the idealized structure. When you decide it, you got to start with idealized structure, and when you build it, you're going to build as the actual structure. If you idealize structure as a fixed supported A, the detail of construction going to be like this. You got to put a lot of constraint into the point A like this. And if you model point B as the rigid joint, you also need to put the construction to be the rigid joint. And by modeling this, most of the time we didn't care about the depth of the beam and the column. We only use the line that's passing to the centroid of the cross section to be our model. And also the force, mostly for the point load, we didn't care about this theory. We just put the force into just a line load. And the support A is fixed and the B is rigid joint, as I mentioned before. Another example, modeling of the steel beam. From this picture, most of the time, this joint is a small beam. Okay, will carry or support the slab that's going to lay above it. The weight of the slab will transfer to the joist, and the joist will transfer the force into the beam. And you model this, you can get the F force at the position of the small beam. And for the support of this big beam, it's up to you detailing. If you detail this one as the roller, you're going to make the slot for the bolt to let the end of the beam move horizontally. However, for the pin at A, you don't need to put the slot. You just make the hole and bolt it. This is another example what we have tested in our lab. We tested the slab to study how it behaves, and then this going to related to the load transfer or load distribution later. Okay, for the slab gonna distribute the force from itself into the smallest beam we call joist. So the joist is going to carry the uniformly distributed load along its length. And by carrying that uniformly distributed load, each joint could produce the point load or reaction acting on the girder or the big beam. So that means this joint is going to take uniformly distributed load. And since the joints separate into inside joints and outer joint, the outer joints will carry smaller area compared to the inner joints. So that means the outer joint carry less force. The inner joint is going to carry large force. And then since the girder will carry the reaction from the joints, So that means this girder will carry 1, 2, 3, 4, 5 load. And the load at the end, at this point, at A and at B, going to be smaller than the load due to the inside joist. And since the 3D picture sometimes is hard to understand, you may draw this into 2 dimensions. So the joists represented by the line like this: 1, 2, 3, 4, 5. And the girder, the AB, is here, and CD is here. The weight from the slab transfer to the small beam or joist. The reaction of the joist act to the girder. Okay, that is going to be the model of our study. For the real thing, which is the indeterminate frame, again, the transfer of the force is very similar to the previous example. The weight from the slab transfer to the beam, the weight from the small beam transfer to the bigger beam, and the weight from the bigger beam transfer to the column, like this: slab, smaller beam, big beam, column. And the model is like this. We also have this frame. That's like you to go over there, take a look at it, thinking about how the load transfer from where to where, how the structure resists the force. Another example about transferring the force, or you may call it tributary loading. Transferring the force of the bridge, okay, the weight of the car transfer to the slab, the weight of the car and the slab transfer to the stinger, and the weight and the force the stinger resists transfer to the forebeam, the reaction from the forebeam transfer to the girder, and from the girder to the column. Okay, this is clearer. The weight of the car transfer to the slab, and the weight of car and slab transfer to the stinger. The reaction from the stinger act on the forebeam. The reaction of the forebeam act to the girder. So it's going to be simplified like this: weight of the car transfer to the slab, slab to the stinger, stinger to the girder, and to the foundation. Mostly, the tributary loading or loading transfer can separate into one-way action and two-way action. Coming back into this point, I should remind you the first examination gonna be talking about the one-way action and the two-way action. I'm only going to make only one problem, so you're gonna be good at both type of action, but I will give you the examination for only one kind of problem. And there are some complicated problems, but the concept is the load transfer from the floor to the beam to the column, like this: floor to the small beam to the big beam to the column, again from the floor to the beam to the column, and then all of them go to the foundation. Okay, let me stop here before we go further to have a small break on this. And next, I will talking about the load transfer, one-way action and two-way action. After I finish talking about this on PowerPoint, I will go to show you how to do by manual calculation. Okay, bye. Okay, hello again. Come to the load transfer or tributary loading. The first, we will start with the one-way action, and then we will move to the two-way actions. First of all, let us consider the structure very simple one here. When we construct the structure, you may recall we start by building the foundation. And then from this picture, you will build the column. When you finish building the 4 column, you build the big beam here and here. And then you may build the small beam cross between the big beam, this one, and this one. So this small beam that we use is support the slab. The slab can be concrete slab or timber floor. It depends. Let's see if the slab have the weight of 0 kilonewton per square meter. What is going to be? When we build it, we build from the ground up. Okay, foundation, column, big beam, small beam, and slab. When we do the load transfer, the load transfer will start from the slab and then go to small beam and then go to the big beam and then go to the column and go to the foundation. So they are in opposite direction, right? Okay. Anyway, when you have the slab, okay, and then it is in 3 dimensions, it's better to make it more simple into 2 dimensions. So at this time, the small beam, this one, EF, can draw like this, like CD and AB. So we have 3 of them, 1, 2, 3. The gray, light gray and dark gray, they represent the floor. Okay. And the big beam, that means FDB. FDB is here, just right here. And another big beam is the ACE is here. When the load transfer from the floor, you can see that the small beam will take portion of the force. If you consider this slab, okay, half of the slab take to the middle beam and another half take to the below beam. And also if you consider the area here, half of this area can transfer to the middle beam and half transfer to the top beam. So that means the beam at the middle will take more forces or more loading than the beam that's on the edge of the structure. Okay, and also the reaction of the middle beam at C and D will be larger than the reaction at the support A and the support B. So the big beam or the girder will get the force large at C and smaller at A and E. Okay, that is the tributary area that's the beam CD supposed to carry, and this for the beam AB and this for the beam EF. Okay, and by doing this, we will idealize the beam CD as the one below here. What do we get? The force. The force comes from the area. Since the area is rectangular, the force is going to be uniformly distributed. How long the beam CD? The beam CD is 4 meters along it, so it's 4 meters. What the magnitude of the load come from? This uniformly distributed load has the magnitude per meter length of the beam. So this means you got to consider per meter length of the beam. For a meter length of the beam, the area that's covered the beam is going to be over here is 2 meters times 1. So it's going to be 2 square meters. Ajahn, where 1 meter come from? Since this is 2 meter and 2 meter length, since the load separate by half, so half of 1 meter is here, and half of this 1 meter is here. So the total of this is 1 plus 1 is 2. So this is 2 meter times 1 meter, so square is going to be 2 square meter. And then when it times with 0.5 kilonewton per square meter, you get for 1 meter of 1 kilonewton. And then the uniformly distributed load distribute to be the reaction. Half of this is 1 kilonewton per meter times 4 meter divided by 2. So 2 kilonewton at C and another 2 kilonewton at D. Okay, the yellow area gonna be half of this, let's see, green area. So the force on the beam CD going to be CD 2 times larger than the force on the beam AB and beam EF. So that means the beam AB and EF going to subjected to the uniformly distributed load, half of this, and the reaction going to be half of this also. Since the reaction of the beam CD is 2 times the beam AB and beam EF, so the reaction of the beam AB is 1, of the beam CD is 2, and of the beam EF is 1. So the big girder gonna support the force like this, which is different from the small beam. And if we test the one-way slab, well, the one-way slab gonna have support on the left and on the right. The behavior of this slab is the same as the beam. So when you increase the force, the crack will occur at the middle of the slab. That means half of this area take the reaction to A, and half of this area take the reaction to EF. So that means the transfer of the force is in the horizontal direction only. So we call it one-way slab. However, when we come to the other slab, it depends on the picture of this one. This beam gonna support in every direction with the reinforcement in 2 ways. Unlike previously the reinforcement is only in 1 way. If you have 2-way reinforcement, you got to consider the length, the L2. Okay, the L2 is the length between the big beam or the girder, and the L1 is the distance between the small beam. If the ratio of L2 and L1 is larger than 2, it's going to have a shape like this. It's going to be the one-way slab. However, if L1 or L2 less than 2, the shape going to be like a square. The distribution of the force is going to be 2-way slab. By doing this, for one-way slab, the distribution of the force is rectangular. All rectangular. However, for the 2-way slab, the force will be distributed to the left and right, and top and bottom. So, by the evidence of experiment, the 2-way slab will transfer the force in the shape like this. On the horizontal, it's going to be in the shape of triangle, and for the vertical direction, it's going to be the shape like this. They are different. So the two-way slab. If you have the two-way slab, for example, over here, the L2 is 6 and the L1 is distance between the small girder is 4, so the ratio is 1.5, is less than 2, so it's two-way slab. With the two-way slab, you're going to separate the slab by using this line of 45 degree. If this one is 4 meter, that means distance is half of that is 2 meter. So the distance this here is 2 meter. And also if this is half of 4 meter is 2 meter, 45 degree is also 2 meter. So this is going to be 2 meter, 2 meter, and 2 meter. The shape gonna be like this. Okay, and since the shape is like this, so the shape of the loading is going to be like this. So where is 1 kilonewton come from? Since the force over here is 0.5 kilonewton per square meter, and the distance over here is 2 meter, so 2 times 0.5, you get 1.0 kilonewton per meter. The other, the pink one, the beam AC, is going to have triangular shape like this. And since this is 2 meter, 2 meter times 0.5 kilonewton per square meter, you get this one is 1.0 kilonewton per meter. And then you can see that if the shape is like this, the beam gonna have the different shape of loading compared to the one-way slab. Okay, I will let you guys have a work on this later, and to at this point I think I'm going to show you how do we calculate the load distribution in the one-way slab and the two-way slab, in order you to have some practice and then do the examination. I recommend you guys to be good on both type of slab to do my examination. Okay, I will show you how to work on the example by writing, and you can study it and practice it to gain more understanding and skill of this calculation. Okay.